ClimateWatch is designed to create an IoT system that monitors indoor climate conditions and smoke levels, offering real-time alerts to homeowners. The goal is to detect fluctuations in temperature, humidity, and smoke, allowing for prompt responses to maintain safety and comfort. In this video, we want to explain the architecture of our software, which is microservices. We have 11 components which mostly developed with Python programming language: house sensors, smoke, temperature, humidity; Raspberry Pi, message broker; DB connector, time series; database, user accounts and controlling access services; the monitoring services; product catalog; the historical data analysis and report; Telegram bot; website. We individually explain these components and outline the data flow, from sensor recording to receiving an alert on the Telegram bot with detailed information displayed on the website. We begin with house sensors and Raspberry Pi components, utilizing the DHT11 sensor for measuring temperature and humidity and simulating smoke detection with test data at regular intervals. The sensor data is transmitted to a Raspberry Pi running the Raspbian Linux operating system. This computer receives all the data simultaneously and publishes it to a specific topic on a message broker. Essentially, the Raspberry Pi serves as the publisher and central processing hub, connecting all the sensors in the project and efficiently sending the raw data to the system's message broker for further processing. In the message broker, real-time communication between system components is achieved using the MQTT protocol. This enables immediate updates on system status to be sent to homeowners and ensures these updates are forwarded to user awareness platforms for further processing. When the Raspberry Pi sends measured data to this microservice, it is initially stored in a time series database via a DB connector. All other components function as either subscribers or publishers. The DB connector, UAC services, monitoring services, Raspberry Pi, Telegram bot, and the website are subscribers to the message broker. The monitoring services, Raspberry Pi, and the product catalog act as publishers to the message broker. As I mentioned, the message broker transmits data to the time series database through a DB connector. The DB connector subscribes to the MQTT topic where the Raspberry Pi publishes data. Once the data is ready for database storage, it is forwarded to the time series DB for storage. The DB connector acts as a bridge between the database and the historical data analysis and report component, facilitating communication through GET and POST API. The InfluxDB data storage database is published as a separate component on a separate server. Until now, the data collected by the sensors has been stored in the database. The remaining components are responsible for analyzing and reporting this data, enabling the end user to be informed about potential risks and to report the data. The website is developed using the C# programming language within the .NET framework, utilizing the MVC, Model View Controller architecture. This design allows users to register and log in to the site, where they can then create and manage various locations, each equipped with specific sensors. Users have the ability to join multiple locations and can filter and view the collected data based on the location and type of sensor. Every user, regardless of their location, is granted the same level of access. This standard access includes the ability to view sensor data, define new locations, and activate or deactivate sensors within a given location. However, there is a higher level of access for a super admin user. The super admin has the exclusive ability to view and modify the overall configuration and settings of the system. Super admin features include managing monitoring settings, editing the database, generating reports, and adjusting both Telegram notifications and general system settings. The UAC, User Access Control, microservice is tasked with managing user data and their access permissions. When a user registers through the site or Telegram bot, the registration and login requests are directed to the UAC microservice. This service handles the verification process. Upon login, the user's credentials are sent to the UAC. If the credentials are valid, the UAC responds with a JWT, JSON Web Token. This token is crucial for subsequent interactions. Any further requests made from the Telegram site or bot to other microservices must include this JWT token in the request header. If the token is missing or invalid, the request will be rejected with a 401 unauthorized error. This mechanism ensures that only authenticated requests are processed, maintaining secure access across the system. When utilizing the Telegram platform and its associated bot, the process of showcasing sensor data involves initiating a request directed towards the historical data analysis and report microservice. This microservice serves as the intermediary, handling the task of gathering and presenting the required sensor information. The historical data analysis and report microservice functions as a crucial link within the system, positioned between the DB connector and various other microservices such as monitoring, site, and the Telegram bot. Its primary role involves retrieving raw data from the database and meticulously formatting it to suit the specific requirements of the recipient microservices. This intermediary not only extracts data, but also ensures its seamless transmission to facilitate effective communication and functionality across the system architecture. The monitoring service regularly retrieves the most recent data recorded for each location from the database at predetermined time intervals via the historical data analysis and report microservice. It then proceeds to compute the average value of data captured by each sensor and cross-references it against predefined thresholds. Should any value surpass these thresholds, the system promptly dispatches a notification to a designated topic within the message broker. Simultaneously, a Telegram bot is actively subscribing this topic and promptly relays any incoming notifications to the user. This intricate system ensures that users are promptly notified of any potential events or hazards within their desired location, enhancing their awareness and safety. The duration between requests made to the historical data analysis and report microservice, the quantity of data extracted for examination, and the average threshold for each sensor are all customizable parameters. These configurations are stored within the product catalog microservice, where we will elaborate on the methods for storage, modification, and notification processes. The product catalog serves as the central hub for managing and configuring all other microservices, essentially acting as the backbone of the entire system. It stores all settings in a single file located on its server, accessible exclusively through the website interface. This catalog not only facilitates configuration, but also serves as the conduit for the REST web service to the website. Operating at the helm, the super admin user possesses the authority to view and modify all configurations. Each edit triggers a request to the product catalog, prompting it to update the configuration file accordingly. Within the product catalog, each microservice is assigned a distinct topic. Whenever alterations occur, pertinent changes for each microservice are disseminated via its corresponding topic to the message broker. This decentralized dissemination ensures that each microservice subscribes solely to its designated settings, guaranteeing the receipt of real-time updates. Thus, every microservice remains perpetually synchronized with its latest configurations. When a user interacts with either the website or the Telegram bot, such as activating or deactivating a sensor within their home, their action triggers a request that is then transmitted to the product catalog. This catalog facilitates the necessary modifications to the JSON file, promptly updating it. Subsequently, these alterations are swiftly disseminated to the Raspberry Pi settings channel via the message broker. Given that the Raspberry Pi consistently monitors its settings thread, it promptly receives these updates, enabling it to promptly execute the user's desired action of activating or deactivating the specified sensor. It's important to highlight that as each individual microservice initializes, it actively retrieves its most up-to-date configurations directly from the product catalog. Subsequently, They autonomously log their presence and functionality by interfacing with the web service. This process ensures that each microservice operates with the latest settings and is seamlessly integrated into the system. First of all, regarding the Raspberry Pi section, the program for this section is developed in Python. Its primary function is to receive data collected by the sensors and forward it to the message broker. During the initial setup of this section, the Raspberry Pi is registered by invoking a REST API from the product catalog, from which it retrieves its configuration settings. Within this component, we have a function called readDHT. This function samples the current values from the humidity and temperature sensors and publishes these readings using a publisher code fragment to the message broker. Additionally, we have a subscriber module in place. This subscriber monitors any configuration changes in the product catalog. When a change is detected, it receives the updated configuration via the message broker and accordingly adjusts its own settings. The subsequent component is the message broker, which continues to be implemented using the Python programming language. This component is responsible for handling data transmission within the system. Its primary function is to receive data sent by publishers, format this data appropriately, and then transmit it to the subscribers who need it. To facilitate this process, the message broker utilizes the MQTT, Message Queuing Telemetry Transport Protocol, which is specifically designed for lightweight, efficient communication in scenarios where bandwidth and power usage are critical. In the DB connector section, utilizing the InfluxDB client, essential queries are executed on the time series database to facilitate both data insertion and reporting tasks. The routes file has been developed to include the required methods and APIs for conducting historical data analysis and generating reports. Additionally, there is a subscriber file responsible for obtaining configuration updates for this section in real time via a message broker. Similar to the process with Raspberry Pi, when this component is activated, it retrieves the most recent configuration settings from the product catalog and registers the microservice through the REST API. In the historical data analysis and report, a comprehensive routes file contains all the API endpoints essential for monitoring and maintaining the website. This file includes two primary methods, a GET method and a DELETE method, both of which are periodically invoked by the monitoring system to ensure proper functionality and upkeep. Additionally, the methods file holds the most recent configurations for this segment, sourced directly from the product catalog. These configurations are crucial for registering this specific microservice, ensuring it operates in alignment with the latest system updates and requirements. In our monitoring microservice, there is a file named methods responsible for registering the microservice. Furthermore, this file contains a job that processes sensor data. This job calculates the average readings from the sensors over specific time intervals, and if the data exceeds a predefined threshold, it triggers a notification to be published to the message broker. The publisher and subscriber functionalities are organized within the classes folder. The publisher file is designed to handle the sending of notifications based on the processed sensor data. Meanwhile, the subscriber file is tasked with receiving and processing the latest configuration updates relevant to this monitoring section. This setup ensures that notifications and configurations are efficiently managed and updated in real time. In the product catalog, the cwconfigurations.json file is located at the root of the project directory. This file contains the configuration settings for all the microservices in the system. When the microservices are initiated, they retrieve their respective configuration details by making a call to a specific API defined in the routes file, which ensures they are properly registered. Additionally, in the methods file, there are APIs specifically designed to handle the retrieval and modification of information related to the house and its sensors. These APIs facilitate interaction with the system and can be accessed via a Telegram site or bot. This setup allows users to easily manage and update sensor data and house information through a user-friendly interface provided by Telegram. As mentioned before, the website part is designed and implemented with C# language and .NET technology and with MVC architecture. In this section, by calling API from other microservices such as the historical data analysis and report, monitoring, and UAC, and mapping the data to the designed models, it displays it in its own views. And when it is necessary to send data to other microservices, this process is done in reverse. In the UAC section, all the necessary facilities for managing users and authenticating them have been implemented, and facilities such as registration and login are provided to the site and Telegram bot through REST API. All APIs are placed in the account resource file, and necessary configurations are placed in the Swagger config file to view and document the APIs. In the Telegram bot, sensor data is showcased through the historical data analysis and report section, where users can also configure the sensors. Upon launching the Telegram bot, the registration process is carried out through User Access Control, UAC, which generates a JWT token. This token is then included in the header of all subsequent requests made by the Telegram bot. This ensures that all requests from the Telegram bot to other microservices are authorized. For the Telegram bot to function, the internet on the mobile device or tablet must be active. If any of the sensors detect suspicious data and send a monitoring alert, the Telegram bot will receive this information in real time, promptly notifying the user of any incidents. As illustrated, adjacent to the Raspberry Pi, there are operational sensors, specifically the DHT11 model, which are actively measuring and recording the room's temperature and humidity levels. Additionally, the smoke levels are being simulated directly within the Raspberry Pi system. In this section, we will conduct a thorough examination of the site, taking into account the different types of users and their respective capabilities. There are two primary categories of users on the site: normal users and super admin users. Normal users have the ability to define new locations and assign specific sensors to these locations. They can also view the data that is recorded by these sensors, allowing them to monitor and analyze the information collected. On the other hand, super admin users possess all the privileges of normal users, but with additional powers. In addition to defining new locations and viewing sensor data, super admin users can access and modify the configurations of catalog products. This includes the ability to view detailed product information, make changes to product settings, and update any configurations as needed, providing a higher level of control over the site's operations and data management. The Telegram bot offers a wide range of site functionalities, including the ability to manage both locations and sensors. However, it's important to note that only the super admin has the authority to alter the overall system settings, and this can exclusively be done through the site itself.